Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Tear, and today this is my fourth lecture in a series on probability and statistics. And today I'm going to talk about a very important topic in probability theory, namely Bayesian statistics. In particular, there's a very important result called Bayes' theorem. This was developed by a very famous mathematician named Thomas Bayes from the 18th century, English mathematician. And it's just a mathematical formula for determining conditional probability. But it's very easy to derive, as you'll see. So here's the formula written now. It says if you want to calculate a conditional probability, this is called the posterior probability of A given event B. So I'll give you an example of this later, but A and B are any two events. So you want to calculate what's called a posterior probability or conditional probability of event A given event B. You don't know that to start with. What you do know is this other conditional probability where you just reverse the events A and B. So you know P of probability of B given A. You also know the overall probability of event A, and you know the overall probability of event B. Well, this gives you a formula for calculating the probability of A given B given all this other information. And it's very easy to derive this formula. And I'll show you the definition in a minute, but let's just back up a little bit. Let's talk about conditional probability. I went over this in my first video on the series of probability. This is just a definition of conditional probability. We say the probability of event A given event B is equal to the probability of both A and B divided by the probability of B. And you can look at some specific examples. I think I wrote this in a slightly different form. Last time I said the probability of A and B is the probability of B times the probability of A given B. I think that was one of the formulas I wrote down in the definition of probability. And I think that should make sense if you think about it. But you can actually write, what's interesting is this is a very easy formula to derive. And here's the definition. They write in this a little bit different form here. Instead of writing and, they say the probability y given x, you can write it in two different ways. You can write it as the probability of y and x times the probability of x, but then you could also write probability of x given y the probability of x and y times the probability of y. But then the next thing you should notice is the probability of x, since x and y and x are the same thing, and is commutative. You can write both probability of x and y and the probability of y and x, which are both the same thing, as a probability of x given y over the probability of y. And then you can just move things around a little bit, solve for the probability of y given x from the first formula, just plug in this formula of probability of x and y, probability of x given y over probability of x, and then you multiply that by the probability of y. That's just your second formula. Voila! That's how you derive Bayes theorem. Pretty easy to derive, just some very simple algebra and definitions of conditional probability and rules for them. So anyway, and this is a very, very useful formula. Despite it being very simple, it's very useful, and it's also a little bit counterintuitive, as you'll see. And you can write it in different ways. There's different ways you can write Bayes' theorem. On top, this is the general form of Bayes' theorem. Probability y given x is the probability x and y divided by the probability of x. But you can expand the probability of x. So, the probability of x, if you have a bunch of variables y, in the second form, this is the most general form. So, for instance, let's say X is, I don't know, X is that it rains tomorrow. And then there could be a lot of different factors. It rains tomorrow if the wind is 20%, 20 miles an hour, if certain conditions hold, if the humidity is over 90%. You can write down a bunch of conditions and you can add them all up as long as they're mutually exclusive. That's how you can expand the number. In particular, if y is some event, I mean, we already have the event y here, so we can expand the probability of x as the probability of x and x given y times the probability of y, plus the probability of x given not y times the probability of not y. This is a very useful form, this bottom equation here. is a very useful form for Bayes' theorem. And I'm going to give you an example, and I'll show you how counterintuitive it can be. So here's a good example. And by the way, Bayes' theorem is used a lot concerning diseases. You know, when you're doing, like, if you're testing, this is a very common application for Bayes' theorem, trying to determine what's the probability that you have a disease if you test positive for it. And most people think that if they test positive for a disease, that pretty much means they have it. And I'm going to show you that that's not at all the case. And here's an example. Suppose you test positive for a disease that affects 1 in 1,000 people, which the probability of a false positive or a false negative is 1%. So there's a 1% chance that the results of your test are wrong, whether or not you have the disease. That doesn't seem like very much, but as you'll see, it can very greatly affect the results. I mean, so you're given that you've tested positive for some disease. Let's say COVID-19. Let's say the latest strain of COVID-19. I don't know what percentage of the population it's affecting right now. I don't think it's very big. It may actually be only 1 in 1,000. But suppose you just decided to see if you have it. So you go to the doctor, you take a test, and then you test positive. And you might think, oh no, I have it. But actually, here's what's going on. There was a 1% chance of a false negative. So I'm just going to label the events here. Plus is the event that you test positive. Minus is the event that you test negative. D is the event that you have the disease. And H is the event that you don't have the disease, i.e. you're healthy. So now I'm going to do I'm going to use Bayes' theorem in that bottom um, equation I showed you earlier. And here's what you get. The probability that you have the disease, given that you tested positive, is equal to the probability that you tested positive, given that you have the disease, over the times the probability that you have the disease. That's what goes in the numerator. And then that's also the first term in the denominator, but you have to add that to the probability of a false negative, that you tested positive given that you are healthy, times the probability that you are healthy. And now let's see what happens when we plug in the numbers here. The probability we tested positive, given that we have the disease, that's a true positive. That's a 0.99% probability, or 0.99. The probability that we have the disease is only 1 in 1,000, 0.001. So that makes this numerator pretty small. And then you write it down again in the denominator as the first term in the denominator. But then there's also the probability of a false positive, and that's 0.1%, given that you're healthy. Well, look at this. There's a 99.9% chance that you are healthy. So it actually turns out to be much more likely that it was a false positive than that it was a true positive, because the disease is so unlikely. I mean, it's a lot more unlikely that you have the disease than it is that you'll get a false positive. That's why this probability, when you actually calculate it, turns out to be so small. When you plug in the numbers, you get about 9%. So you only have about a 9% chance of having this disease, even if you tested positive for it. And a lot of people don't realize this. A lot of people, they get really, really panicky when they notice that they test positive for a rare disease. But what they're not realizing is that it's much more likely that it was a false positive than that they have the disease, especially if it's a very rare disease. So that's an important application of Bayes' theorem, and that just kind of shows you how, even though it's a very simple result in probability theory, it can lead to very counterintuitive results. So anyway, that's my video on Bayes' theorem and Bayesian statistics. I hope you enjoyed it, and I'll see you next time.